All right, so we're gonna finish Power Series in the next section today. The next section is called Taylor and McLaurin series, but they are essentially Power Series as well. And so we sort of started this already last Thursday, right? So last week, and so I wrote down the definitions again, right? So these are the two definitions of Power Series. And so if you look closely, and as I already mentioned this last time, power series is essentially an infinite term polynomial, right? So it's basically a polynomial with infinite number of terms. And essentially what we're going to try to do is we're going to try to represent functions as power series, right? And that's eventually where we're going. That's eventually where we're headed. And that's basically what we want to do with power series. So now there's a couple of things associated with that then. And so one is you want your function values to equal your power series values, right? So obviously they have to be equal to each other if you want to represent a function as a power series. And the other one being if they are equal to each other, that means the power series is going to have to converge somehow, right? So it has to be converging at the very end, which means it has to have a sum, okay? And so the first thing we're going to take care of is if you have a power series, we want to know where it's going to converge, right? So for what values of x, remember x is your variable, you're going to plug that into your function. And so that means you want to be able to get a value out of it in terms of your power series. And so you want to know where, for what x values are your power series are going to converge. Now, with that said, there are going to be three possible outcomes. And so the first one being, it has to converge at the center. Right? So it's only going to converge at the center. So which means it's whatever x equals a is for the first version, right? Because and then the other one is x equals 0 because that's the center for the other one. Now, how do we know that converges? Can you tell me if you plug it in, right? So if you plug in a into each one of these, right? Right, the polynomial is going to equal what? You can type it in the chat if you want to. Right, so if you plug in a to the polynomial, or in this case, 0 for all your x's, okay, the result is going to be what? So if you plug it in here, right, a minus a is going to give you 0, right? This is going to be 0 and 0. So all you have left is c naught, which means there is a sum, right? So the sum happens to be c naught. And so that means it's going to converge at x equals a. Right? So that's one possible option. That's the only way or the only place where it's going to converge. The second option, or the second case, is all real numbers, which means we are talking about negative infinity to positive infinity. And then the third case, it's going to converge for some values around x equals a. So let's say x minus a is less than r. So it's sort of a r away from your center. Okay. And so now, okay, so those are the three possible cases where your power series are going to converge. So now, how do we determine this? So let's do an example. So example number one, right? So essentially determine the interval of convergence and and the radius of convergence. Essentially, this is what R is. So R is your radius. So over here, R would be infinity. And then for the first outcome, it would be R equals 0 because you don't go any farther away from your center. Okay, so those are the interval of convergence and essentially the radius of convergence for each one of those cases. And so the first one, right, so example number 1. And so I have the power series from n equals 0 to infinity of x minus 1 to the n power all over n factorial. All right, so from here, right, so we can use essentially pretty much anything, any of our tests that we sort of went over in the previous sections. Now, obviously, we want sort of absolute convergence, right, because we don't want to see if it's conditionally going to converge or sort of not. And so we want to test for essentially absolute convergence. So that leaves us essentially with two possible options, which means it's either going to be your ratio test or going to be your root test. Now, since it involves factorials, and more likely than not, we're going to deal with a lot more sort of rational functions. We sort of don't want to use the nth root, right? Because it's an nth root. It is a little bit easier to do your ratio test. So we are going to essentially perform your ratio test. And so if you don't remember how the ratio test works, right, you take the limit as n approaches infinity of the ratio of consecutive terms, an plus 1 over an inside the absolute value, and then you get a limit, right? And so the idea is if L is less than 1, it converges, which is what we want, right? And then everything else, right? So L greater than 1 diverges. And then when L equals 1, it's inconclusive. Right? But obviously, we want it to converge. So the first one is well the result we want to get. So now let's go ahead and set up the ratio test for our power series. And so we take the limit as n approaches infinity. Okay. Again, it's a fraction already. So this ratio, I'm going to write it as a product, and then the bottom would be the reciprocal. So you'll have x minus 1 to the n plus 1 all over n plus 1 factorial. And then the an is exactly this. You just now have to divide it. So you have to do reciprocal. So n factorial over x minus 1 to the n power. Any questions so far? You can always unmute yourself and then just ask the question. Okay. All right, so now, okay, obviously simplifying, right? So we spent some time on this the week before. And so the n plus 1 factorial and the n factorial will reduce. Right? And that would give me with an n plus 1 at the bottom. Okay? And then over here, right? So n plus 1 power and n. So that would reduce all of that. And that leaves me with x minus 1. Right? So now this is the leftover so far. So we have limit as n approaches infinity, the absolute value of x minus 1 over n plus 1 inside the absolute value. All right, so now from here, you're gonna have to pay attention to your variable, right? Because now there are a couple of variables that we are worried about, right? So we have the x variable for your power series, and the reason the x is there, because remember, this would be a function, okay? So the x is going to be there. The other one is the n, right? So n is the variable for your series, or in this case, summation notation. And so n is the variable for the summation, which is if you now pay attention to your limit, n is the one that's going to infinity, essentially the x minus 1 is considered a constant because it does not have n in it. And so I can factor that out of the limit. And so this essentially is the absolute value of x minus 1 times the limit as n approaches infinity of 1 over n plus 1 as a ratio. Questions? All right, so now you take the limit as n goes to infinity of a rational function. The top number is fixed. The bottom number is going to go to infinity. And so 1 over infinity is going to go to 0, and 0 times anything is going to give me 0. So the limit is 0. So now the question is, when is 0 less than 1? Well, that's always. So it's always less than 1, okay, which means it's always going to converge regardless of what x is. So which means the interval of convergence is negative infinity to positive infinity, and then the radius of convergence is infinite, right? Because 1 is your center, and then how far is it from infinity to negative infinity? Well, it's infinite. So which means this ends up becoming your answer. Questions on that? Any questions? All right, so I want to try another one, right? So I want to show you one where it's 0, and then I want to show you one where it is an actual value from both sides, right? So, so let's look at some more examples. All right, so example number 2. So it's the summation from n equals 0 to infinity of, let's do n factorial times x to the n. And so again, the setup is always try to do a ratio test. Now, since there are no fractions here, I will write them, or at least the limit, as a fraction to be the limit as n approaches infinity of the absolute value. So n plus 1, so it's n plus 1 factorial, x to the n plus 1, right, all over n factorial x to the n power. And again, start reducing. And so, so the n plus 1 factorial would give me n plus 1 on the top. The x to the n would give me an n left over the top. So this is now the limit as n approaches infinity of n plus 1. And since there are 2 terms, let me put parentheses on there. And then times x. Again, the same thing's going to happen here, right? So your variable is x. So that can be taken out of the limit because your limit only is for n. And so now doing the same thing or the similar thing as before. So it's going to have to stay out inside the absolute value. The absolute value has to be there for the x because we don't know what the value of it is. So absolute value of x times the limit as n approaches infinity of n plus 1. So again, since n is always positive here, the absolute value is really not necessary. So now you take the limit as n goes to infinity. Okay. Well, this would be infinite. So now the question is, when is this less than 1? Well, you're gonna say, oh, it's never because it's infinite, right? So, so you'll say never. Okay. Now remember, there is still an x over here.